In this next section, we discuss the most fundamental of organic compounds, the alkanes. We will pay particular attention to the structure of these molecules as well as how to name them. So, as we've already seen, an alkane is a compound which contains only carbon and hydrogen in its structure, and furthermore, it contains only single bonds between the carbon atoms. The alkanes always have formulas of CN, H2N plus 2. So to make this clear, what this simply means is whatever the number is after carbon, you double that number and add 2 to it to find the number of hydrogens. So the simplest alkane, CH4, after the carbon is a 1, we double that, so 1 times 2 is 2, add 2 to it, and you get 4. That's the formula. C2H6, that's because if you double 2, you get 4, add 2 to that, and you get 6. 3 times 2 is 6, plus 2 is 8. What if we had C20? Well, 20 times 2 would be 40. Add 2 to that and you would get 42. So the formula for C20 would be C20H42. They are very important to us as the main component of our fuels. They are extremely nonpolar, as we would expect, and they do not mix with water in almost any case. Oil is made up of alkanes, and we've already seen from personal experience that oil, of course, does not mix with water. Cycloalkanes are very similar to alkanes in terms of their chemical reactivity. The big difference is cyclo means that these compounds have rings. And so we're going to use the term cyclic to indicate that they have rings when you hear that word. So a cycloalkane contains at least one ring, and the formula of cycloalkanes, instead of being CnH2n plus 2, is just CnH2n. So for example, if we have a carbon with a 5-membered ring, so C5, H would be 10. You just double the number. We often encounter compounds in organic chemistry that have the same molecular formula, but their atoms seem to be connected differently. The term to describe these molecules is structural isomers. So it's a relationship word, just like brother, sister, sibling. We say that molecules are structural isomers of each other if they have the same molecular formula, but the connectivity between their atoms is different. So let's take a look at these two molecules right here. They are definitely alkanes. There are 4 carbons, so that means there must be 10 hydrogens. Again, how did I get that? 4 times 2 is 8, plus 2 is 10. So if we added these numbers here, we'd have 3 plus 2 is 5, plus 2 is 7, plus 3 is 10. So this is C4H10. This compound over here, by quick inspection, you will see is also C4H10. They clearly are different. If we go ahead and we take a look, for example, the most obvious difference is this carbon here has only 1 hydrogen on it. There is no such carbon on this molecule right here. All of them have at least 2 hydrogens. Similarly, this molecule has 3 carbons with 3 hydrogens on them. The molecule to the left has only 2 carbons with 3 hydrogens on them. So this means they're likely to have different properties, and they're also going to have different names. Let's take a look at these two molecules. We already saw this one on the previous slide, but what about this one? It turns out that even though I have bent the structures of this particular molecule, it is exactly the same as the structure on the left. We can prove this by essentially just going carbon by carbon and seeing that they match up. So if I start with this carbon here on the left, CH3, that's the same as this carbon here, CH3. it's bonded to CH2. Well, that CH3 is bonded to CH2. This CH2 is bonded to CH2. Same thing over here. And then that CH2 is bonded to a CH3. Same thing over here. So the technical word for the relationship between these is conformations, but the most important thing to recognize is that they are identical compounds. They are not different. And when we get to naming, we'll see that they have exactly the same name, butane, either way, so that means they must be the same compound. Let's explore this in a little bit greater detail. To demonstrate this concept a little bit further, I'm going to use a piece of software here which is called ChemDraw, which I use to represent most of the molecular structures in these videos. So this is that molecule butane that I was talking about just a moment ago. Let me go ahead and make a copy of it. So we agree these are exactly the same. But now I'm just going to move atoms around. So I'm going to move that CH3 up to there. This molecule, other than that bond being a little bit too long in my opinion, is exactly the same as that one. I didn't break any bonds. All I did was twist a bond to produce this particular structure. So these two are identical drawings. Same molecule. Let me copy this one. Let's say I go ahead and take this carbon off to the right with its hydrogens, and I drag it up there. This is still exactly the same compound as the other two that we have there. Let me take these guys here and drag it down to here. And let me take this carbon and drag it all the way around. Again, it's the same structure. No different. What if I took this one again, and I'm just going to go ahead and take the whole molecule and rotate it 180 degrees. Almost. It's still the same. Ultimately, by bending these bonds, I could always get back to the same structure. No bond breaking would be necessary. So there we are. Here we are. Boom. Boom. So I never actually needed to break any of those bonds to get back to exactly the same structure. Now let me consider another structure for the time being here. Alright, that's a very ugly way of drawing a structure, so let's go ahead here and put the carbons in. Not much better. Let's go ahead and pretty it up, and there we go. Now, no amount of bending will change this structure into any of these molecules here. There's simply no way to do it. I can bend these around, I can pull these down, I can do anything I want. There's really just no way that I can change one of those into the other, even though these structures all have C4H10, no matter what. So that tells me that these must be different compounds. The only way I could get this compound to be this one would be to actually change it. I would have to change the bonding. And once I change the bonding, it's no longer a structural isomer. I'd have to actually break that bond. Off it goes. And you see it took one of the hydrogens with it. And I'd have to make a totally new bond to get the other molecule. Okay, so, going backwards, we see that this molecule is a structural isomer of this molecule here, which has just been represented multiple times. Let's get rid of some of them. There we go. And so these are two different molecules. It turns out for the formula C4H10, these are the only two possible ways of drawing the formula correctly. Remember, carbon must make 4 bonds, hydrogen must make 1 bond. Therefore, these are the only 2 methods. And I urge you to practice with that. Try seeing if you can come up with other structures. And if you think you have, either it's an incorrect structure or it's one of these and you've just missed it somehow. I promise you, there is no other way. If I, again, rotate this, same thing, just drawn on its side. Rotating it again, same thing. Rotating it again, same molecule. Okay, let's practice this concept. So I would like you to take this molecule here, which now has 5 carbons. So 5 carbons means it must have 12 hydrogens, correct? 5 times 2 is 10, plus 2 is 12. So this compound right here, which we'll see is called pentane. And I want you to come up with 3 different ways to draw the same identical molecule. So it's 3 different ways to show CH3 bonded to CH2, bonded to CH2, bonded to CH2, bonded to CH3. So we would again call those conformations. So 3 in addition to this. Then I would like you to go ahead and draw 2 isomers of this compound. I'm just going to use the word isomers from now on. I'm not going to introduce another kind of isomer for a long time. So in order to make these isomers, remember, it can't have the same connection of bonds. It still has to follow the rules. Carbon still has to be making 4 bonds total, but it can't be this exact same pattern. There are only 2 other isomers of this compound, so I need you to carefully practice drawing new connections, breaking these bonds to come up with 2 isomers of the compound. This might take a while, so I'd like you to pause the video and we will go over potential solutions for this when you come back. So I'm going to go back to using ChemDraw to illustrate these different parts. So part A asks you to draw 3 different conformations. So the same compound here, but just 3 different ways. You only need to do 3 different ways. I'm going to do several here. So let me copy that. And first thing I'll do is take this first group here and twist it up. And unfortunately, that makes it a little bit ugly. So let me move it down and do that. There we go. And let me take that one and I'm going to copy it. So same compound here. Let me go ahead and twist these 2 up. And again, you saw none of those lines broke. They just twisted with me. Make those a little bit shorter. But none of the lines broke. So, so far we have 2 in additional to the starting one. Let me go ahead and take this one and I'll take it over here and let's see what I can do. I can take this and twist it down. So there's another conformation. Let me go back to the starting one. And I'll go with a zigzag kind of a look. Let's take those down. So there's part of a zigzag. Let me take it again. And actually, no, that's quite good. Let me just drag this down here. Now, if you look very, very carefully, this structure looks a lot like this structure over here. All it is I've taken it and rotated it. Okay? It's the same structure. So all of these are identical, and there should be a few more ways that you can twist this around. In fact, there should be many. Oh, let me take this and switch it around right there. And you see now this is very much similar to the structure above it. So these are, again, all identical ways of representing the exact same compound. If we named them, we'll find out they are all named pentane. There's no difference between them. For part B, I need to make actual isomers. So the way to make isomers is I actually have to break bonds to come up with different structures here. So let me go ahead and try this. Best way to do this is you just break the last bond. So let me just get that last bond broken right there. So now I still have my 5 carbons. Let me move this. I can't move it to the first carbon, because if I did, I'd just end up with that top structure right there, and we already saw that's the same molecule. So can't do that. But what if I put it on the second carbon? And made a bond. Aha! This is certainly different, because it's the, of all of these molecules we see drawn on the page, it's the only one that has a carbon with only a single hydrogen atom on it. So that means it has to be different than certainly this structure over here. Again, it's got 5 carbons, and it has 12 hydrogens. We can verify that. Now, this is where a lot of people will start coming up with, new ways of doing it that are actually the same molecule. So, for example, let's say we're going for the next one. You might say, well, let's just continue what I just did a second ago. Let's break that bond. Move this carbon to the 3rd carbon in the chain. And say, aha, I have a new one. But no, you don't. You've been deceived. If you were to go ahead and we were just to rotate this around, and then I was to have my software flip this upside down, see, it's exactly the same as that structure right there. So that would not be a new isomer. So what we have to do is we have to start coming up with yet even more creative ways of how we might come up with another structure. And let's try this. What if we break that bond, and let's move the carbon to bond with that middle carbon right there. Aha! That is also different. Let me make this look a little bit nicer if I can. Well, it doesn't want to look any nicer. But if we go ahead and look, this is definitely different, because here we have a carbon bonded to 4 carbons. It has no hydrogens on it, which is totally different from these over here. And again, if we check, there's 5 carbons and 12 hydrogens on this structure, so it must be an isomer of the others. There are no additional isomers for C5H12. These are the only isomers, and you can, this has been mathematically proven. You can try to come up with additional ones, and I promise you they are essentially the same molecule. If you think you've come up with new ones, then essentially all you're doing is, rotating groups around like I've just done there, or like I've just done here. But it's still the same molecule. And as you'll learn shortly, when you name compounds, it will have the same name as what it was before. I'm going to finish off this video by taking a look at some of the fundamental properties of alkanes. The first thing that we want to consider is the boiling point of an alkane. Recall, the boiling point is the temperature at which a liquid turns into a gas. So it depends on a couple of factors. The first is the size of the molecule, meaning how many carbons essentially it has in it. And the next being the amount of branching that we have in the molecule, and we'll focus on branching again in a second. So the first factor, the more carbon atoms an alkane contains, the higher its boiling point. So for example, pentane, which has 5 carbons in it, C5H12, boils at a higher temperature than butane, which has 4 carbons in it, which boils at a higher temperature than propane, which has 3 carbons in it. So the more carbons, the higher the boiling point. Now, many of the alkanes have branches, and when we talk about branches, that means that a carbon which has more than 2 carbons attached to it is a branch. So any carbon bonded to 3 carbons is considered a branch. Any carbon bonded to 4 carbons is considered as having 2 branches, as opposed to chains. And a chain is just when you have a carbon with 3 hydrogens bonded to one with 2 hydrogens, bonded to another one with 2 hydrogens, and so forth and so on until it ends with a carbon with 3 hydrogens. Turns out chains have greater surface area, and that allows the molecules to attract each other. If you remember, there was a name for that force of attraction between those molecules. Those were called the London dispersion forces. So in general, the more branching there is in a molecule, that means it has less surface area and it will have a lower boiling point. So long chains have higher boiling point, very branched carbons have lower boiling points. Let's examine this further with an example. So going back to my ChemDraw software, I have here again the 3 isomers of C5H12 that we just saw a moment ago. So this is an example of a molecule which is strictly a chain. It has CH3, CH2, 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 CH3. There is no what we call a branching point on this. This isomer does have a branch being a carbon which is bonded to more than 2 carbons. So this carbon is bonded to 3 different carbons. So we say it has a branch. And over here we could say that, well, here the chain is 3 carbons, and it has 2 branches off of it, 2 branches off the same carbon. So we would say that this compound here is even more branched than this carbon right here. So let me just use some arrows here to point out the branch. So that's 1 branch, and there's 2 branches. And so if we were to go ahead and rank these here, we would expect the compound on the left to have the highest boiling point, which it does, of these 3. And then this compound of the 3 would have the lowest boiling point because it has the most branching. And the compound in the middle would have a boiling point in between these 2. As I said in the beginning of the lecture, alkanes are nonpolar. They only contain bonds between carbon and hydrogen. Since carbon and hydrogen have this roughly the same electronegativity, very close electronegativities, we say that they are nonpolar molecules. So we would not expect them to be soluble in water. Water is, of course, polar. And they are less dense than water, at least in every example I can think of off the top of my head, and so we would therefore expect them to float on the surface of water. And we can think about oil slicks for an example. I'm going to stop here and delay talking about naming of alkanes to the next video. Thank you.